Hello, everyone. Welcome to the second paper on the track 3 today. It is coming from Oski Technology from Yeung. And the topic of the today's paper is level 4 formal verification with end-to-end checkers and abstractions. Let's go live for the session and we'll come back for the question and answers after the session.
Welcome to DVCon India 2021. So in this presentation, we're going to talk about level 4 form verification using end-to-end checkers and abstractions. Now, the work in this presentation was based on the experience of Oski Technology. So for the past 10 years, Oski Technology has been using level 4 form verification to verify some of the most complex blocks in their customers' design successfully. So for the agenda, we're going to start explaining the different usage level of formal verification. Then we will be focusing on level 4 formal verification. So there are two major components. One is the end-to-end checker. Another one is abstraction techniques and modeling. We will conclude the presentation with 3 test cases, and we will explain how we verify them using level 4 formal verification. So formal verification has multiple usage levels. We start with assertion-based verification using one of the assertion language, such as system verilog assertion. We encourage designers to put assertions into the RTL code to capture the design behavior. Now, for some user, the assertion language may be difficult to learn. That's why EDA vendor has introduced formal apps. Formal apps will generate the assertion and verify those assertions automatically for the user. And to make things even easier, there are automatic formal. Automatic formal is like linting. The checks are encapsulated inside the tool, and the tool will look for common design issues inside the RTL code. So formal verifications at level 1, 2, and 3 are very good at bug hunting. They enable RTL designers to find bugs very early in their design cycle. However, they are not sufficient to sign off a block completely. That's why we introduce level 4 formal verifications. Level 4 formal verification replaces simulation, and it enables designers to sign off a block completely. A few paper has been published previously about level 4 formal verifications in DVCon and other conferences. They talk about how level 4 formal verification can be used to verify blocks such as the load store unit, warp synchronizer, cache controllers, multi-link aligners, and MAC-RX blocks. Beyond level 4 formal verifications, there's level 5. This is the system level architecture verifications. It uses formal verifications to verify special system level concerns, such as a system level deadlock, cache coherence, and system level securities. So for the rest of this presentation, we will be focusing on level 4 formal verification. So let us take a look at the methodology used for level 4 formal verification. So the idea is to verify the block exhaustively, and the quality of the formal run will depend on 4 components. So first of all, on the left-hand side is the end-to-end checker. So end-to-end checker is very important to capture the end-to-end behavior of the design. So we are not talking about just capturing one hot or simple properties of a design. We're talking about capturing the end-to-end behavior of the design. So those end-to-end behavior basically represent the specification of the design. So by verifying the end-to-end behavior, it makes sure that the design is working correctly. And the second one is constraint. So we want to make sure that formal are using the legal stimuli to verify the design, and also property will be proven given the input constraints. The complexity is an area we will spend a lot of time to focusing on during this presentation. So if you have been using formal for a while, you will have noticed that sometimes it's very difficult for formal verifications to converge on some of the complex complexities inside design. So that is the area we use abstract model a lot. So we use abstract model to help formal verification to exhaustively verify some part of the design and to handle the complexity problems. And finally, for coverage, with formal tools from different EDA vendor, we can measure formal coverage on statements, on branches, and on state machines to make sure that formal verification has been verified the design comprehensively. First of all, let's just take a look at the end-to-end checker. So the end-to-end checker was developed using the design specification. It is like a reference model to the original design. So sometimes developing the checker could be as big an effort as writing the RTL code. So on the left-hand side over here, we have an RTL block. So the end-to-end checker will monitor the input to the RTL block and the output to the RTL block. A protocol monitor will be used to constrain the input side, and then another protocol monitor will check the output side of the design. The monitor will also be used to extract data from the input stimuli, and those data will go into the checkers. Now, the checker will perform similar operation just like the RTL blocks, so it will compile and store the expected result. So once the data is available on the output of the RTL block, we will extract the data, and then we will compare that with the originally pre-computed result, and make sure that the RTL block is performing the operation correctly. Now, on the other hand, if we implement the checker just like the RTL block, the checker will be as complex as the RTL blocks. So that's not very good. So as a result, while we are developing the checker, we will look for ways to simplify the operation of the checker. And at the same time, we will deploy abstraction technique we will talk about in the next sessions. Now for the checkers, we purposely divide the checkers into 4 parts: the input handshake, the output handshake, the control path, and data path. Now one of the reasons for doing this is allow multiple team members to work on a different part of the checkers concurrently. But much more importantly is by doing this, we can deploy different formal algorithms and approach on different part of the design. So for example, we can first focusing on the data path of the design. So we can use a special formal algorithm to verify the data path of the design. And then when we are verifying the control part of the design, we can black box the data path elements inside design. So this enables us to handle much more complex design and also enable us to do a divide and conquer approach. Now, in addition, abstraction model can also be used to simplify the design. So for example, if there is long latency elements or storage elements inside design, such as counters, FIFOs, or memories, we can use abstraction model to replace those components and simplify the formal models. Next, let us take a look at a few abstraction techniques. First, case splitting. Case splitting is more like a divide and conquer approach. It decomposes a complex design into multiple formal runs, and each formal run will focusing on a particular configurations. So as a result, it reduces the cone of inference and the state space of each formal run. Cut points and black box are very common and very popular. It eliminates logic driving the cut point and also the logics inside the black box. These cut points and output of the black box becomes control points for formalifications. We cannot constrain them accordingly. Next, resettable registers and counters. Now, they are very common elements inside a design. However, sometimes it may take a lot of transactions to load an interesting value into a register or count a counter up to a certain value. So reset and counter abstractions are very useful to short-circuit this process. It allows formal to control this element more directly. So these approaches help reduce the formal depth required to verify some interesting activities. Abstraction modeling is very useful for handling complex data elements inside design. So for example, in the networking and data transportation design, there's a lot of symbolic data elements inside design. So instead of representing the multi-dimensional arrays of data elements, we only need to represent a single dimensional abstract models. So it will certainly reduce the cone of inference and design space for formal verifications. So for example, in the RTL code, we may have a very complex system Verilog elements and a long array of it. So instead of representing this long array of system Verilog elements, we only need to represent one symbolic location. By keeping the symbolic location constant, we are writing and reading from that single locations only. Now, since this symbolic location is unconstrained, formal verification can explore the complete address space and exercising all the possible scenarios. So one very good examples are memories inside design. So instead of representing the two-dimensional memory structure inside design, we only need to represent one element of the memories. So by keeping the symbolic location constant, we are reading and writing from that single locations inside the memory. So FIFOs are very common design elements inside a design. However, a deep FIFO has a very negative impact on the formal performance. So we want to define abstract models for the FIFOs. We do that by defining a symbolic depth. A symbolic depth is less than the actual depth of the FIFO. We keep the symbolic depth stable throughout the formal run. Now, instead of using the actual depth to determine the rollover condition, we use the symbolic depth to determine the rollover conditions. So since the symbolic depth is unconstrained, formal location will explore all the possible value for the symbolic depth. It will use a small value if possible. Now, by using this approach, we will hit the FIFO full conditions much sooner than before. That will allow for modification to verify what happens when the FIFO is full and overflow. Abstraction modeling is very important to reduce the complexity of the design and also the latency required for formal verification to reach deep into the design. So we have covered some of the commonly used modeling approach for symbolic data, FIFOs, and memories. We don't have time to cover the data independency approach using the Whooper coloring approach or the tagging modeling, but the details are in the paper. You can take a look later. As mentioned earlier, level 4 formal verification sign-off consists of 4 components. End-to-end checkers are used to capture the end-to-end behavior of the design to make sure that the design is implemented the specification correctly. Constraints are used to control the interfaces, and abstractions and abstraction models are used to achieve convergence, and then coverage are used to measure formal coverage. Now, as we have implemented the checker constraint and as we are running formal verification for a while, we want to ask ourselves, are we done yet? Now, to answer the questions, we want to review whether our checkers has complete. Have we captured all the design specifications in the checkers? Are we complete all the requirements, etc. And for the constraint, we want to make sure that the constraints are weak enough. So we may have a very tight constraint initially, but as we are completing the project, we want to make sure that we are not over-constraining the design. And also, the complexity strategy is complete or not. We want to make sure that whether formal reaching deep into the design, and also we want to make sure that the bounded proofs are sufficient. Now, if those are insufficient or formal has not exercised all the behavior of the design, so we may want to add extra abstractions into the design and then to give formal more flexibility and control of the design. And finally, we want to look at the formal coverage to make sure that the formal coverage goal has been met. First, let's take a look at a parameterized multicast crossbar design. So this is the design we used in Break the Test Bench Challenge in DEC 2005. Now, in this 8x8 multicast crossbar design, each client can send requests to any target or multiple targets, and each target has an arbiter to decide where the request get forward based on 3 different levels of priorities. Now, during the event, 73 RTL bug has been inserted into the design. Now, all of them has been exposed by one or more checkers. So this is an excellent exercise to demonstrate that end-to-end checker is very comprehensive and it can catch, if there's a bug inside the design, it will catch it. This is also an excellent example to demonstrate how we can use abstraction to simplify the end-to-end checker test bench developments. Now, compared to simulation, in simulation, we probably would have to write checkers for 64 different pairs of clients and targets. Now, in the formal test bench, however, we are using symbolic variables to represent the client and the target and implement all the checkers for that symbolic client-target pair. So for modification, we'll explore all the possible values for the symbolic variables and ensure that none of the client-target pair will fail. We partition the test bench into control path and data path. So for the control path of the test bench, we have multiple checkers. We have an arbitration checker to verify the arbitration scheme, a consistency checker to make sure the grant is given correctly, and a perform checker to make sure that operations are performed correctly when the condition is met. So for the data portion of the test bench, we have a data integrity checker. The data integrity checker makes sure that data is going from the input to the buffer and then from the buffer to the output port correctly to either ensure data is not corrupted, duplicated, reordered, or dropped. Now, since the data is not transformed, this is a perfect case to use the woofer carrying scheme. It doesn't require any data storage. Now let us take a look at the process we went through to build the end-to-end test bench. Now, since the design is not very complex, we do not need to perform any divide and conquer. We are focusing on the functionality of the design, so we prioritize the data correct list, and then the arbitration scheme, and finally the sequence of operations in the design. To implement the end-to-end test bench, we first start with the interface. So there are two interfaces in this design, one on the client side, one on the target side. We capture the interface using protocol monitors. Now for the checkers, as I mentioned earlier, we separate the test bench into control path and data path. So we have arbitration checkers to verify the arbitration scheme. We are using the woofer carrying technique to verify the data integrity. We also have a forward progress checker to make sure that operations are performed when the conditions are met correctly. And for the abstraction technique, we are using the symbolic nature of the design, the client and the target. So we are using symbolic value on the client and target pair, and Formal will verify all the combinations. So to sign off this design formally, first we integrate the protocol monitors into simulation. So if the monitors are over constraining or incorrect, they will fire in simulations. And also, we have in this particular event, we have found all the RTL bugs inserted. So this is a very good and demonstrate that the end-to-end checkers are very comprehensive. And since the design is not very complex, we were able to achieve 100% coverage on both statements and branches. The second design is a level 2 cache request coalescer unit in a GPU design. So there are 6 virtual channels that are processed in parallel, and the flow is credit-based, with credits issued by the L2 on a per VC basis. So the problem is in a design like this, the top-level simulation will never exercise the block sufficiently to verify the potential deadlocks inside a design. So blocks with embedded store condition may introduce dependency and as a result deadlocks. So in this case, we developed a special end-to-end checker to detect circular dependency in the store conditions. So this circular dependency checker will exhaustively traverse all entries in the dependency table and detect all possible loops. So to reduce complexity, symbolic variables were used to enable fortification to select the initial store block and process the rest. So this end-to-end checker has been implemented successfully to verify that this design is deadlock free, and also it can be used for future projects. Next, let us take a look at how we developed the end-to-end test bench in the 3 phases. So in the planning phases, since the design is complex and there are multiple blocks in the design, we took a divide and conquer approach. We implement different test bench for different submodules inside design. So in this case, there's a test bench for the request module, and there's a test bench for the respond module, and there's a test bench for the top levels. Then we prioritize the functionality of the design, all the functionalities, and all the IP blocks in the design, and then we implement specific checkers for each of them. And to reduce complexity, first of all, we black box one of the submodules, and the submodule will be verified independently. And for FIFOs and CAMs inside the design, we shrink the design size. And then we also partition the VC path to reduce the latency. Now to implement the end-to-end formal test bench for this design, we first start with the interfaces. There are 2 major interfaces in this design. One is the crossbar interface, another one is the L2 interfaces. We use protocol monitor to capture the interfaces and at the same time constrain the input port. Now for end-to-end checker, there are multiple functionality we want to capture to make sure that they are correct. So first of all is the request coalescing, the data integrity, the response replay, and the forward progress checkers. Now since the design has very long latency, we have to use multiple abstraction techniques such as the counter abstractions and the Woven method for data consistency. And for modeling, we use a symbolic address for the CAM. So for formal closure, we have integrated all the protocol monitors into simulation to make sure that we have not over-constrained the design. At the same time, all the monitor has been cross-proofed among modules to make sure that they are consistent. So during the process, we have identified 57 bugs, and 7 of them has been recognized as corner case behavior that will never be found by simulation alone. Now, when we first start measuring formal coverage, we are not even close to 100%. But as we are developing more and more checkers, and also we make sure that we have checkers on every output port, so finally we were able to get 100% coverage on both line and conditions. So the final design is a network on a chip configurable cache controller. Like many cache controller we have verified before, cache controller has many corner cases and has many configurations. Simulation alone is not able to deliver the level of confidence for productions. Now to verify this cache controller, and one of the decisions we have made very earlier on to handle the design complexity is to create 2 separate test bench. So we have created one formal test bench for the tab type and another formal test bench for the data pipes. We maintain a very clean interface between them. We capture those interface in properties, and then we cross-proof those properties to make sure that they are consistent. Now, also to handle the complexity of this design, we have used abstract modeling to handle the memories inside the design. So for this configurable cache controller, we don't have time to go through the test bench development phases in details, but you can find all the information in the paper. However, I want you to focusing on the end-to-end checker and the abstraction techniques. Now for the end-to-end checkers for the tag pipe, we are using end-to-end checkers to verify the tag state machines, the eviction address, and also the replacement policy. Now for the data pipe, we are using end-to-end checker to verify the write-read data integrity and also the eviction data. Now the design is complex, so we are using a lot of abstraction techniques that include reset abstractions, cut points. As mentioned earlier, we are using symbolic set for the tag and data memories. Now for data consistency, we are using data coloring. So finally, to summarize, we have described level 4 formal verification using end-to-end checkers and abstractions. So clearly, it can be used for block level formal sign-off. There are 2 major benefits. First, it reduces time to finding the first bug because it enables you to verify your design as soon as possible. Second, it reduces time to finding the last bug because it enables you to verify your design effectively and thoroughly. So finally, we also acknowledge the support of our management team and engineering team in India.
Hi, Mr. Ping. Thank you for your session on end-to-end level 4 formal verification. I have a few questions listed here. First question is, we're talking about level 4 end-to-end verification, but some of the approaches listed are similar to what also gets used at level 3 and other places also, right? So what is specific differentiation you consider from level 3 to level 4 end-to-end checker, except for the scalability and complexity of adding more checkers and interface security?
Yeah, the real difference is that we are starting from the design specification. So we use the design specification to create the end-to-end checker. So we don't look at the RTL code at all. And also during the process, because the design is complex, so we use the abstraction models and divide and conquer approach to verify the design end-to-end.
So, okay, and that leads to the second question, which you initially also talked about the effort involved in creating these models. It's as complex as RTA development. So, being that complex and to do it end to end, so can you throw some light on the effort involved in making this subsystem or IP verification? How much was the time taken, and was it in synchronous to the RTA development?
Oh, that's a very good question, actually. Actually, we normally we want to engage with the RTL team as soon as possible. So while the RTL team is writing the RTL code, we want to create the formal model at the same time. So normally we have 1 or 2 people assigned to partner with the RTL designer to work side by side, but we don't We don't look at the RTL code. So we develop the formal model on the side. But at the same time, we do the formal model as already presented. The formal model does not need to be completely as accurate as the RTL code. We use abstractions and also to simplify it. And also, as you already mentioned, that we also partition the control path from the data path elements. We also black box some part of the design which can live unconstrained for formal.
Okay.
But I certainly do not want people to underestimate the effort required.
Yeah. How do you sign off on bounded proofs?
That's a very good question. Actually, we had a paper talking about how we calculate the bounded proof. So normally we calculate. I think I also mentioned that not in this presentation. I mentioned that in a separate paper. Is we look at we calculate the bounded proof based on the coverage information, based on the firings, and based on the complexity of the design. So there is 5 or 6 different parameters we use to calculate the bounded proof.
Okay.
Yeah. So for people who are interested, feel free to contact me and I can follow up to give you the details.
In the symbolic depth method, are you replacing the memory and FIFO depth completely? What is the trade-off?
We are replacing the FIFO depth completely and the memory completely. Yes, that's right. So the trade-off is that the main reason for doing that is to allow, it simplified the model for formal, but it did not reduce the accuracy because as a symbol, formal has complete freedom to explore any symbol value. So formal can pick any symbol value and use it to verify the design. So if one particular value will cause a failure, formal will find it and then use the symbol that will cause a failure. So the counter example will consist of the fail symbol that caused the entry to fail. So it reduces complexity, but it does not sacrifice accuracy.
I think extending to that, I think how would it be different by using symbol versus doing a loop of all variables? So which one is better? But how is it exactly reducing the complexity?
Yeah, because if you create a loop of all the variables, that the formal model it built will be n square instead of n, right? It will be it will be a 2-dimensional array instead of 1-dimensional array. So the formal model created by the tool will be huge. That's cause problems, definitely.
And one final question. So can you give an example of a simulation resistant bug that you discovered, or any example specific scenario, or what is simulation resistant bugs that you uncovered through this level 4 verification method?
Oh, okay. So that is covered in another paper as well. So so the formal method, because it's an end-to-end, and also is the end-to-end checker is developed based on the specification. So a lot of time it covers a lot of corner cases, normally not exercised by simulation. Now simulation, when we write a test bench, we are focusing on the positive behavior of the design. So we are focusing on sending transactions into the design and make sure that the data is correct and things like that. So for simulation, we are focusing on the positive behavior. Now for formal is very good at exploring the negative behavior or corner case behavior of the design. So because the formal look at all the complete spectrum that should be allowed. So unless you constrain it, formal will explore everything. So formal can find a lot of corner case situations. So a number of the superbug, we call it superbug, basically happen because there are multiple combination of events happening at specific time that trigger a bad behavior inside the design. Now, for simulation, even though you are doing constraint random simulation, sometimes it's very difficult to hit those corner case situation accurately to explore the bug. So Formo can do that.
Thank you, Mr. Peng, for your time and presentation. Thank you.
Okay, thank you.